Hello, everybody. Good afternoon. I first of all thank you, especially the organizers of this conference, for kindly inviting me to present the works which we do in our research group and with my collaborators as well. So this specific work is about electron MHD turbulence, which is basically done in collaboration with Professor Amita Das in IIT Delhi and Arijit Haldar, my PhD student, who is also present here, has also taken the lead role in this paper. So turbulence and the universal cascade, since I think that many people here use turbulence and plasma turbulence, but their way of thinking the turbulence is really different. So I want to just present what we in general do when we talk about turbulence. So basically, as we all know, the turbulence is a flow regime where the nonlinearity largely dominates over the viscous properties, and which is equivalently can be seen as a regime with very high, infinitely high Reynolds number. And then when the turbulence is fully developed, that means the system is totally nonlinear and you have many structures, and mostly if you think of the famous pictures, you will always think the structures to be mapped to ADs or vortices, okay? So those type of things, when you have full of such things in your system, then you can actually see that you have ADs or vortices of different sizes, and that actually shows the multi-scale nature of turbulence. And in this type of flow, Kolmogorov made some phenomenological idea, and he gave actually by the help of the picture already provided by Richardson. So he said that the energy is given in this type of systems at the large scales, and this energy will be transferring from one scale to the other scale by nonlinear transfer without any dissipation, okay, across some intermediate scale. And finally, they reach those scales which are very small and give some dissipation due to fluid viscosity effects. Okay? And this method of non-viscous transfer from one scale to the other is traditionally known as the cascading of the quantity. And people can show that if a quantity is inviscid invariant of the flow equations, for example, to energy, helicity, okay, if they are inviscid invariant, they are actually very good, like potential candidate for being to cascade. Okay, so here I am just showing you a very schematic picture of this, and this where this biggest eddies are actually getting fragmented due to incompressibility to the smaller scales, and finally you will have the smallest possible eddy size where exactly the dissipation starts, and this is known as the Kolmogorov scale. So basically, between this forcing scale and the dissipation scale, there is a scale called the inertial scale where this cascade is acting. You can show, you can define the largest scale of that inertial zone to be called as the integral scale, and the smallest scale to be the Kolmogorov scale. Okay. Now, for hydrodynamic turbulence, this type of universal cascade property is most popularly like understood in terms of an energy spectrum, okay, which scales as k to the power minus 5/3, where Ek is the spectral power density of the kinetic energy, because here for an incompressible hydrodynamic fluid, the kinetic energy is an inviscid invariant. You can do the similar thing for kinetic helicity, which is another inviscid invariant. This type of thing, we can show that is true, that Ek is scaling as k to the minus 5/3, but actually, analytically, you cannot derive that exactly. These are all phenomenological results. Now, analytically, if you really start from the first principles, Navier-Stokes, and you consider the conservation of energy in the inviscid limit, what you can actually show that a linear scaling relation between the third order structure function of velocity and the length scales, and that actually called the exact scaling laws. It is exact because you derive them under some hypothesis, okay, but you derive analytically. So now, for homogeneous and isotropic incompressible hydrodynamic turbulence, which are the basic assumptions of turbulence, one can show this type of scaling law to be exactly, this is the third order structure function. L actually gives you the velocity fluctuation along the direction of the measurement corresponding to a scale L. Okay? So the cube of that is exactly equal to minus 4 by 5 epsilon L. And if you are inside a Kolmogorovian inertial zone, that epsilon should be independent of scale. That means that this quantity is actually linearly varying with L. Okay? If we just relax the assumption of isotropy, we actually obtain an equivalent divergence form for the exact relations of both energy and kinetic helicity, and these are called the more general divergence form of exact relations, where you can see that they are no longer projected along the direction of the measurement, but they are now written in the vectorial form. You take the divergence, and this L is also vectorial L now, okay? And that is equal to minus 4 epsilon. Now, if you are again in the inertial zone, this epsilon is constant, then you can now, in isotropic condition, you can integrate over a sphere, and you can get a scaling relation of this type. You can do same type of thing here for the kinetic helicity, but here only changes, instead of V, the main advecting agent here is the omega, the vorticity vector. Okay? Now, for length scales, very, very larger than the ion inertial length, a plasma is also described as a fluid. Now, it's true that the people who are really working with different scales plasma, for them, suddenly talking of fluids is a little bit disturbing, especially where the collisions are not, negligibly small. Then it is really a question. However, in this case, I can show you that sometimes it is also possible that if your scale, so let's say you are taking a collision-less plasma or weakly collisional plasma, but you are now talking of a very large scale over which you are seeing the fluctuations, still you can think of a fluid model. That's the essence of having fluid model here. And if the length scale is very large, then we can even describe by a center of mass fluid, where the inertia is governed by the ion fluid itself, and it is called the magnetohydrodynamics. This is the ordinary magnetohydrodynamics, or MHD. Now, for homogeneous MHD turbulence, equivalent exact relations are given by Politano and Pouquet. You don't have to go to the details of the equations now. You just see that all these equations are involving 2-point increments of this V and B. B is the magnetic field, okay? Now, what is the importance of doing those exact relation other than the aesthetic feast that we have Kolmogorov universality? The only thing is that this epsilon is basically, finally, also gives you the turbulent heating rate due to this cascade if you have a stationary regime, okay? That also you can show analytically. However, the exact relation for the third invariant, which is magnetic helicity, the third invariant of incompressible MHD cannot be written in such a beautiful form under a divergence. Okay? Here this is for the total energy. The second one is actually for the kinetic helicity, the cross helicity, which is the volume integral of V dot B. Okay? So that's why people thought that maybe there should be a better way to write those exact relations even. So same problem also occurs when you are even talking of the cascades of energy and helicity in Hall MHD turbulence. You cannot write under a very beautiful divergence very easily. Now there is a trick we have also recently discovered, but when this problem occurred, then there was no solution priori. So what we do, basically, before going to show a good solution for an alternative exact relation, let me tell you what we do in general as a recipe to derive these exact relations. First, we search for the inviscid invariants, okay, in a system. If we find them, then we construct the 2-point correlators of those invariants, okay? Because if you now take the Fourier transform of that, that will give you actually the so-called energy power spectra corresponding to that scale, okay? Because you have to, the interesting point about turbulence is, in turbulence is not the single point variables which matter, it is actually the 2-point correlations which are mattering, because every 2-point actually manifests a scale, and in turbulence it's the scale or the structure size which is finally mattering. Okay, then we calculate the time evolution of the correlators, okay? That is also time evolution of the Fourier transform of the spectral density, as I just said. They're equivalent. And finally, we consider a statistical stationary state where the time derivative of the correlator vanishes. Okay? Now, this is something a little bit non-trivial. This is a statistical stationary state which is a scale dependent. So that means you have to really wait for sufficiently long time where exactly where you can actually suspect your inertial zone is there. For all those scales, at least stationarity is achieved. Okay? Now, we first consider, after this statistical stationary state, we first consider inside this ourselves inside the inertial zone where the viscous effects are negligible, and then finally you equate the average forcing rate to be equal to the energy injection rate, and then your exact relation is obtained. Considering the stationarity, neglecting the viscosity, and finally taking the forcing as your energy input, these three steps are non-commutative. So you have to do in this specific order. That is related to the famous dissipative anomaly. Okay. In order to get rid of the aforementioned problems, an alternative form is proposed which enables us to derive the exact relations for homogeneous turbulence without using the divergence form that I did during my postdoc. Still with my PhD supervisor, and those gave you some type of relations where you can see there's the energy cascade is now given by this one, the helicity cascade is given by this one, and for MHD, the total energy cascade is given by this one. What are the interesting points of that? Those type of relations immediately shows you every turbulent state, switched on turbulent state, as a finite departure from the Beltrami aligned states. So for example, that means that whenever you are talking of Beltrami aligned states, turbulence is somehow partially or totally killed. Here you can see a Beltrami alignment, immediately your turbulent cascade is killed. That means, in other way, that you can always think that Beltrami aligned states will be the relaxed states. Okay? Here you have different combinations of alignments which can finally kill the total turbulence, but only one type of alignment cannot kill the total turbulence. A schematic view, especially for people who really want to know how to work on these regimes theoretically. So this is now the scale picture, okay? So it actually says that you have so this is the forcing scale, the largest possible scale. So in this scale, the only way you can change the correlators is just by using the forcing, okay? Now, the second part, the transfer part, is not yet conceived, not yet perceived by this part, because if you remember, already the transfer part has a divergence. So there is a scale over, right? Okay, it's a gradient is there. So that's why this one is switched on when you are going a little bit smaller scales, and then you have two things. You have this as a source term from the large scales, and this is the transfer term. Now you have two options. You have a stationary state, okay, where you actually keep on forcing. That means this is non-zero. So that gives you a stationary state in long time, and you have exact scaling relations, okay? And this one is actually the part which relates to the epsilon I showed you. If you cut the forcing, basically it has a transient non-stationary state, and finally, so all of this is actually non-equilibrium steady state. So then there is a non-equilibrium non-steady state. It relaxes towards a stable equilibrium steady state, okay? Or equilibrium steady state. So which is the final relaxed state. In those regime, the turbulent cascade is off. No nonlinear transfer in average. Still, the fluid is now just moving, dissipating, okay? Because it is taking all this transfer rate thing as input, and now it is just dissipating. So now you just think that at this point, if you suddenly switch the forcing off, this thing as off, so that is the relaxed state finally, your thing will be simply a diffusion equation. It's a linear. So no non-linearity on average, normal relaxation, okay? Based on this, we have given a very general theory on fluid and plasma relaxation, which was published in 2023. So this is the electron MHD system. I have to accelerate a little bit. So for weakly collisional plasmas, we can still consider a fluid model where we can consider the fluctuations at smaller scales. Smaller means how much? Sufficiently smaller than the ion inertial length. That means at those scales, you don't expect ions to move. It is only the electrons move. Why this is somehow a good model to explain some aspects of collisionless plasma? Because if you see, in collisionless plasmas also, ions are so rare. You can also think that they are not existing, and only the mobile electrons they are moving. So you can see that although they are not theoretically equivalent, many aspects can be actually explained by also this electron MHD. And mostly the turbulence thing actually is very, very interesting, because the turbulence regime, which is totally governed by the nonlinearity, often becomes equivalent to a normally what you can expect from a collisionless plasma. Now, for such a fluid model, the ions are practically immobile, and both the inertia and current are given by the electron fluid. You have a quasi-neutralizing background by the ions, which are heavier and cannot move in these scales. So you have actually a very interesting equation, which is J equal to minus NeVe. So the fluid velocity is now directly related to the curl of the magnetic field, given we are neglecting the displacement current under non-relativistic limit. That also gives you another gift in plus. So that is, in addition, that gives you the incompressibility condition of the electron fluid by construction. So then the governing equation becomes like this. Okay? So this is the whole equation for the electron fluid and the Faraday's equation. Okay? Here you can have two types of dissipations. Okay? And finally, if you smartly eliminate E from these two equations, the electric field, finally you are given by this equation, which is an equation with this new variable, dE square, nabla square B minus B. Okay? I call that Q. Okay. So now the first thing is that we have to search for the inviscid invariant. In three-dimensional incompressible EMHD, we have two inviscid invariant. One is this one, the total energy. Another is the conjugate helicity, P and Q. Okay? So where P is this and Q is exactly the curl of P, which if you calculate, you will see that will exactly be. Now, you exactly follow the recipe what I said. For stationary electron MHD fully developed turbulence, you will get two beautiful scaling laws. I mean, exact laws, not yet scaling. Which are given in a very compact form like this. So this is for the total energy cascade, this is for the total helicity cascade. Okay? The effect of background magnetic field is found to play little role in determining the turbulent effect, because of this term exactly goes to 0 if you have a uniform background magnetic field. If the background magnetic field itself is non-uniform, then you can have some effect, of course. Attention, we should not search for a hydrodynamic limit just by making B is equal to 0, because this is not a fluid plus magnetic field, because here the fluid velocity itself is equivalent to the curl of B. Okay? So it's a magnetically coupled fluid. It's an electron fluid. Okay? So when I cut the forcing, basically what happens that you have, again, using the method of this energy and helicity vanishing cascades, you have a very small relation which you can have. It gives that the curl of the cross product of VE and this quantity is exactly equal to gradient of phi. And if you now think that this is an arbitrary, this is actually an arbitrary function. So it is coming because the original condition is curl of the cross product of these two is 0. From that, this is the most general one. Now, if you assume this to be 0, then you have a double Beltrami relaxed state, which is usually found theoretically for Hall MHD. For weakly collisional plasma, the question is that, so in order to somehow understand that whether the energy cascade is Kolmogorovian or not, we have to make sure that the epsilon has a constant regime. That means across some scales, epsilon is constant. Okay? And for that, we developed a pseudo-spectral code, DNS code with 512Q grid points. This is done in Paramsanganak IIT Kanpur, which is the HPC. Okay, so this is the time integration we have performed using fourth order Ranjit-Gupta method. We have used a non-helical forcing just to concentrate on the energy cascade. The next step is, of course, to use helical forcing like ABC. And we have used hyperviscosity because of our limited resolution. Since we are using pseudospectral code, we have to use 1/3 dualism, whatever with the convention. So only the 1/3 is actually surviving. And that's why we wanted to make somehow a non-polluted inertial zone, but also at the same time, we cannot use much larger hyperviscosity. Otherwise, your delta T or the simulation unit time steps will be very, very small, and you have to really wait for long for the simulation to develop, turbulence to develop. And we also put random magnetic field as initial condition. You can see the two boxes. This is B, this is UE. UE means this is also the current. That's why you can see finer structure here, a little bit coarse structure over here. This is the guarantee that I have reached somehow, more or less, okay, with this moderate resolution.
So Pratik, 3 more minutes.
Yes. To a statistically stationary state, and then this is the box of this again, the slice B and UE, where the stationarity is achieved, that is 15 times the nonlinear time. So first we show, before examining the exact law, what we do, we actually calculate the power spectra, and the power spectra are very much matching with the phenomenological prediction. That means here, for the scales which are less than, which are larger than the DE, okay? This is in the K space, okay? Larger than the electron inertial scale here, you see? There actually, you can always find a Hall type of -7/3 scaling. So this is a compensated scaling, of course. And here you find a Kolmogorov type of -5/3 scaling, but for the electron fluid. Finally, with all these things, we are all set for checking this Kolmogorov thing. And then we actually, when we calculate epsilon using our exact law for the energy cascade, we found that in this range, finally you can see there is a constant flux. And then the question is whether this is Kolmogorovian. Yes, EMHD turbulence has a Kolmogorov universality. So individual terms, if you see, that is only the kinetic energy term, this red one, okay? And this green one is the magnetic energy term. Kinetic energy term means electron kinetic energy, okay? Electron fluid. And they are individually not constant. It is only the sum which is constant, okay? So that is also to understand here. And this is the dissipative term in purple, you can see. So the dissipative term becomes dominant in the very small scales, which I have not shown here. This is the relaxation part. Now at 16 NL, we have taken data at 15 NL, time nonlinear, okay? And at 16 NL, we cut the force, we let the system relax, and you can see that all the nonlinear terms are relaxing much more faster than the linear, all the nonlinear transfer terms, they're actually decaying much more faster than the individual quantities themselves. That is actually a signature of our recently proposed theory. The question is still that whether we can see U cross Q is grad phi or U cross Q is 0. That arbitrary grad phi will be 0 or not. If it is 0, that is called an aligned state. If it is not 0, it is called a Grad-Shafranov type pressure supported state or pressure balanced state. So Arijit did it brilliantly. So he first calculated the angle between U, E, and Q. This Q is exactly equivalent to the capital Q. This is only written in the Alven units. Okay. So Alven units, non-dimensional units. Yeah. So if you do that, you can actually see that if you are going to 17 nonlinear, 33 nonlinear, and 50 nonlinear times, relative importance of this cos theta +1, -1, they are more or less decreasing. So that means the alignment is hampered. On the other hand, if you do the Karl calculation, you can see that is actually with larger time increasing. So that's why this is the cos theta, okay, between these two terms, M and K. M is this, okay? But they are, in Fourier space. That shows that a pressure balance state is much more likely. So this is the conclusion. You can see we have derived an exact relation for EMHD turbulence. Using the method of cascade vanishing, we predict the possible relaxed states. Using DNS, we found a clear signature of Kolmogorovian cascade, and the relaxed state comes out to be non-aligned pressure support state. We are now ready with 1024 cube grid point codes. I think Arijit is ready, right? Okay. So local and non-local transfers will now be examined for the same system, and I am searching for a motivated postdoc who can handle those simulations and also a little bit of analytics. Okay? Thank you very much.
Thank you. So floor is open for questions, please.
Hi, thank you for the nice talk. I have a question regarding, so your dissipation scale is for, okay, your dissipation scale, can you hear me now?
Relaxed state.
No, your dissipation scale.
Dissipation scale.
Yes, is far smaller than the electron's inertial length scale.
Here the system is, yeah. So the electron inertial length scale is in between. Ion inertial length scale is much larger, and dissipation scale is really even smaller.
Exactly. So your system size is more or less at the order of ion inertial length scale. Your dissipation scale is far smaller than the electron inertial length scale.
Correct.
Right.
Correct.
Now your system is weakly collisional.
I am not saying, look, that's what I'm saying. Many features can be of weakly collisional system can be described by EMHD turbulence. EMHD itself, EMHD, a fluid is not weakly collisional. Don't mix. What I'm just saying that certain aspects of collisionless phenomena in nature can be mimicked, even with something which is theoretically not equivalent.
Okay, okay, thank you. And what could be the astrophysical kind of relevance or places that we can verify or you can have your...
Very, very good question. I purposefully give you a very brief answer now, okay? In solar corona, you can have in solar corona and also in solar surface plasma, okay? You can have very strong type of strong reconnection, which are not Pesek, neither Pesek nor Sweet Parker. Turbulent reconnection is the only possible way to solve. Yes, if you are interested, I can talk to you after this. This is the very good question. Yeah. Thanks for this.
So, very good talk, as usual. So, this prescription that you have given,
yeah.
Suppose you introduce a helical forcing. Right now, you have done a non-helical problem. So, if you introduce an helical forcing, like a dot, I think you said in between the talk, ABC like flow,
yes.
and use that as a forcing.
Yes.
So, it will become large scale because helicity will connect larger regions of...
Large scale with respect to this system.
Yeah, with respect to this system, it will become large scale. So, now we know that there is a finite A dot, equivalent of A dot B being conserved, right? Helicity will be conserved. In this case, generalized helicity will be conserved.
Yes.
So, do you think that the whole procedure will prescribe a new set of relationship, or?
We have, in fact, Arijit took the lead role. We have made a good picture. Actually, this is very difficult, because you know, like this is a self-helicity, but generalized part. So, with respect to the directions, there are always some ambiguity. We have now made a good picture. Arijit can show you, and we can also show. So, there are completely limits, and actually, you can show all the characteristic length scales. DID, either they act like a source of helicity or a sink of helicity. If it's a sink of helicity, this is called the helicity barrier. If it's a source of helicity, then you have dual cascade from this.
So you expect similar thing to come out?
Yes. Limit should do, yeah.
Okay, thank you very much.